So we want to talk about solving the distributed constraint satisfaction problem. Now, first, we're going to just talk about the constraint satisfaction problem. And so here, the most common way to do it, the first way we're going to show is I'm going to show you how to use depth first search to solve this problem. But first, I want to talk about the graph coloring problem, because it's the example I'm going to be using. So in the graph coloring problem is an instance of a constraint satisfaction problem, and it's very simple. You have a graph like this one, nodes and edges. And the problem is you want to color it, so you have also a set of colors. You can have just two colors, black and white, or three or four, whatever. And you have to color the graph. You want to find a coloring for the graph, so each node is going to be a color, red, blue, green, whatever, such that no two adjacent colors have the same, and no two adjacent nodes have the same color, right? So you can have red, red, or blue, blue, whatever. And that's the graph coloring problem. Notice it is an instance of this. It's like a limited constraint satisfaction problem because all the constraints are between two nodes only. Or in the more general constraint satisfaction problem, constraints can be between any number of nodes. So you could have, these four nodes have to be a different color, which you cannot do in graph coloring. Well, unless you tie them all up together. And you can have, so there's certain constraints you cannot express in graph coloring, but nonetheless, it's easy to visualize, it's easy to see, so we're going to use that as an example. So let's say we want to color a graph, find the coloring for a graph. We can use depth first search, right? So the basic algorithm is fairly straightforward. It's a recursive algorithm, as you notice here. And the idea is basically we start with a node, we color it, then we go to the next one, and the next one, and we keep doing that recursively, as long as we can find a color for the next guy. If we ever cannot find a color for the next guy, we backtrack, and then we try the next other color for that guy. Right, so that's what this is doing, the recursive call here. So the easy way to visualize this is with just a graph. So we can draw basically the call graph. So what you're going to have is at the first level here. So we call it here. The first one, this is going to be the first node. I'm just going to call him N1. And let's say he is the color blue. And then he's going to recursively call. And now we're going to be at N2. And so let's say, again, he's the color blue. Let's say N3. This one calls recursively. And now he's the color blue. Let's say at that point that we detect that, oh no, he can't be blue because a constraint is violated. So we're going to return and we're going to tell N2, oh, no, that didn't work. So N2 is going to have to try to be red. And maybe that doesn't work either. So N2 goes back. It's like, oh, I'm sorry. Goes back to N2. N2 says, okay, you got to try again. N3 tries green. So we try green for N3. That doesn't work. We backtrack over here. Say there are only 3 colors for N3. So now N2 has to try a different color, which is going to be red. So I'm going to add that there. And then after that, maybe N3 tries blue. And we say maybe at that time it works. So blue, N1 blue, N2 red, N3 blue, it works. And so we're done. So we would be done. Otherwise, we'd keep backtracking. So, and in the worst case, right, which is the case when there is no solution, depth first search will do the whole tree, right? So depth first search is complete algorithm, right? So that's why we call it complete. This is depth first search is complete. So, that means, if there is no solution, it will tell us. So it will tell us, oh, there is no solution, or it will find a solution if there is one. It will stop at the first one, but you can easily change it to find all solutions. So it's complete. It will tells if there's no solution, but of course it takes a long time. The reason we like it, we could have used breadth first search or some other types of searches. And one reason this is a good sort of place to start is because we search N1, N2, N3. But we could do this in any order, right? This will work regardless of the order in which we search these. But, it turns out that it helps a lot. You can speed up the algorithm by properly sorting these. organizing that. So, generally you want to put the more constraint nodes towards the top. More constrained nodes should go towards the top, um, because that way you hit the wall earlier, and so you backtrack earlier, and so you end up searching the top part of the trees, and you don't have to go deep. Um, and so people do, because of that, people use a lot of heuristics and try to help improve the basic algorithm, for their particular domain. So the particular ordering is going to depend on your domain, etc. But depth first search is very easy to modify because of that. And also, it's also nice that it uses very low memory. So depth first search has low memory needs, computer memory I'm talking about. So because you only keep the particular stack that we're working on, unlike depth first search, we don't have to keep the breadth of the tree. We only keep that one. So it can be, you can solve fairly big problems with it. So those are why we use them. Why people use this, and it's a good starting point for a lot of more complicated algorithms. Now the main problem for us in agent systems, multi-agent systems, is that it's not really distributed, right? So we're talking about distributed constraint satisfaction, but DFS is very much a centralized solution. There's no obvious way to distribute it, right? So you pretty much you assign N1 to blue, N2, and then N3. You have to know the previous assignment, so there's no obvious way to distribute it. It's kind of by itself. It's a centralized algorithm. So let's talk about a distributed algorithm instead.